I'm going to tell you a little bit about what you have been doing in this program called Symmetry, Thermodynamic, and Topology in Active Matter. It was supposed to start on March 16th as a real program and got first temporarily postponed and then started as a virtual program. Now, many of you may know that in 2014, we actually had a 4.5 months program on active matter with 2 Blackboard launch talks. You can go and look at them online. Today is a new world, so we are going with a virtual program, and as you can see, a whiteboard talk instead of a Blackboard talk. I guess with virtual lunch, at least for some of us. And we are now in the 8th week of the program. And before I start, I want to make sure to thank the KITP staff that has been really wonderful, stepped in with a couple of days' notice and starting recording all our talks. First, active matter. My title, first of all, active matter and why does it matter? I should actually make sure to thank my co-coordinator, Sriram Ramaswamy, from whom I actually stole this title. He probably is not attending the talk right now since he's in India. It's pretty late for him. So I will start by telling you a little bit what active matter is. It describes the systems that are out of equilibrium, and I will try to tell you why it is different from other non-equilibrium systems. I will mostly do so by focusing on a particular example. So in this talk, I will mainly focus on 2 items from the title, symmetry and topology in active matter. I'll leave thermodynamics alone for now. And I will illustrate that in the context of an example of an active fluid that generates its own flow. And then I will conclude by just very quickly mentioning some of the questions and that the virtual Active 20, now in its 8th week, has been trying to address.
But Cristina, if I may interrupt, but if you could just try one more to let some people in.
Okay.
See if there's anybody out there. I'm getting emails from 2 people.
Okay, I admitted all that were there now. Let's see. I think there might be another one just arrived.
Sorry about that.
It's okay.
Imagine the back of the room and people are just clamoring to get in.
Okay. So what is an active particle, first of all? An active particle is any particle, any entity that consumes energy to generate forces or drive its own motion. And of course, there are many examples from the living world. An example could be a bacterium, or of course any other type of living cell, a bird, one of us, a human. Also motor proteins, those are tiny proteins that are inside cells that actually transform chemical energy into mechanical work, driving, for instance, the motion of our muscles. And there are also examples from the non-living world, that is man-made active particles. And an example is what we could call a microswimmer propelled by a self-catalytic reaction. So if you take, for instance, a gold bead about micron in diameter and coat half of it with platinum, and immerse it in a fluid, in a solution that contains hydrogen peroxide. The platinum serves the catalyst for hydrogen peroxide and breaks it into oxygen and water, generating an excess of products on the side of the platinum and the lack of reactant, the hydrogen peroxide. And as a result of these 2 gradients, essentially, there will be surface forces and slip velocity generated on the platinum side that drive this bead that we call an active colloid to move at some speed V0 that depends on the concentration of hydrogen peroxide, and it can be often of the order of, say, 15 to 30 micrometer per second, so it's pretty fast for this particle, which is a micron size. It's actually very comparable to the typical speed of some bacterium like E. coli swimming in a fluid. So this type of synthetic, this is an example, but there are many other realizations of these synthetic micro swimmers. I need some things. Synthetic micro swimmers or active particles or active colloids, as we call them, are very useful because it allows us to do controlled experiments in a lab. So again, an active particle is any entity that is internally driven, generates its own motion by dissipating energy, and of course, as a result, carries what we could call an error of time. Because of this self-propulsion speed, the dynamics of an individual active particle is not time reversal symmetric, and the particle travels in a directed fashion. So that's an active particle. What about active matter? Of course, active matter is a collection of interacting active particles, sort of a machine made of machines. And in some sense, active matter was first defined by Leibniz back in 1974, when he defined an organism, or a natural machine as he called it, as a machine in which each part is a machine. Yeah, okay, I got the, I think it was 17 something. I think I got the rate wrong. Okay, sorry about that. As I said already, each active particle breaks TRS, time reversal symmetry, locally, and it does in a way that is sustained, and therefore is very different from a system where you apply an external field. Say you have charged particles, and you apply an external field. These particles, of course, also an external field, an electric field, say, also breaks time reversal symmetry, but it does so globally, the same for all the particles. So it's different from these active systems, which are made of components that are driven individually. Now, the focus of our program has been especially on what we call emergent behavior. That is the collective behavior of these active systems in the spirit of Phil W. Anderson, More is Different article back in 1972. And given Phil Anderson died just very recently, I just wanted to mention it in this context. What we are aiming to is asking ourselves whether we can describe active systems as materials. And using the language we use in condensed matter physics, that is the language of symmetry, order parameters, phase transitions, and so on. Keeping in mind that now we have to deal with a peculiar type of phase transition, not just non-equilibrium ones, but ones that are not tuned by an external parameter, such as temperature or similar, but often are tuned internally by the system itself. So, by the way, feel free, please, to interact in questions. I cannot see anybody, obviously, but just speak up, because there is no way I can do this and also follow people raising their hands on Zoom. Specifically, I want to talk, as I mentioned, about active fluids. So these are fluids that set themselves into motion. An example, again, could be a suspension of bacteria swimming in a fluid. The whole fluid, bacteria and solvent, is an active fluid, a fluid that can set itself into motion. And one of the surprises of the field is that we can actually use hydrodynamics. We can use continuum theory that we are familiar with to describe fluids based on symmetry, conservation laws, and such, augmented by terms that describe the energy input due to the active drive. But the very fact that this type of models, which are quite generic, they tend to describe systems of very different type, very different length scales in a unified way. The fact that this type of models can actually work and make some progress to describe the system is already per se somewhat surprising. So let me now be more specific and tell you about a specific model of this emergent behavior. The simplest type of emergent behavior, of course, is collective motion. A bunch of bacteria or a bunch of birds, or all moving together in a synchronized and a coherent manner. The simplest model of collective motion is one that was developed some time ago due to Tamás Picsek, who essentially said, well, let us think of an active particle simply as an arrow. And so a bunch of active particles will be a bunch of arrows that can point in any direction in the plane. And I will, to be specific, I will actually consider here only things and models in 2 dimensions. So we are restricted to 2 dimensions. So an active particle is an arrow that can point in any direction in the plane. That reminds us a lot about a model of magnets called the XY model, where spins, either sitting on a lattice or not, are allowed to point anywhere in the plane. On the other hand, if you have an XY model in 2 dimensions, there can be no order in equilibrium, meaning you cannot have a state where the spins on average all point in the same direction and the system has non-zero magnetization. And that remains true even if the spins are not on the lattice and are allowed to move around. But what is different about our active particles is that the vector, the spin, is now the velocity of the particle. So it's also the direction in which the particle moves. And in this case, you can actually define a rule-based or agent-based model. That's what Picsek did. Simply by saying that each one of these particles or spins aligns, looks at the neighbors and aligns with them. But there is some noise. In the alignment, these particles make some mistakes. The result is that what you get is that when the noise is sufficiently low, or the density of particles, and therefore the number of neighbors that each particle sees is sufficiently high, you actually get a phase transition The order parameter is the mean velocity, which you can really define as the average velocity over all the particles, perhaps divided by the number of particles. There's some plotting there. I will plot it as a function of the noise. So if the noise is weak enough, you have a state where the mean velocity is non-zero, and then it goes to zero above some characteristic noise. So this is a state where everybody is moving coherently. We call it a flocking state, because originally this was the model was actually developed with the idea of describing curve flocking. So that's an agent-based model. But we would like to talk about field theories, hydrodynamics. So how can we do that? Well, there is a corresponding continuum model that was developed by John Toner and UI2 in 1995 that essentially describes the same physics by writing down a continuum equation that merges the physics of fluids, of motion, Navier-Stokes equation, with the dynamics of magnets. Now, I would like to try to write down this equation for you. So it's an equation for the velocity and density of these swimmers, of these particles. The equation for the velocity looks a lot like a Navier-Stokes equation. You have advection, you have gradient of pressure, where the pressure depends on density, rho. You have some energy cost for changing the direction of the velocity. But you also have a damping here, because this is not really a velocity, it's also an order parameter for the system. So this term is sort of almost like a nonlinear damping. But as we see, is a term that allows us to set up the flocking state. And of course, the number of particles is conserved, so the accompanying equation for the density is simply a conservation law. It says that the rate of change of the density is the divergence of the flux. So these two equations are very reminiscent of Navier-Stokes equations. This is supposed to be a P for pressure, okay? Other than for this term, which is of course the term that controls the homogeneous stationary states of the system. And what we find is that if the coefficient alpha is positive, then the only steady state homogeneous solution is one of zero velocity. But if this coefficient alpha becomes negative, there is a steady state of homogeneous solution, which is, I will call magnitude V naught, and some direction, let's call it X, which is picked spontaneously, because this is a spontaneously broken symmetry of the system. Of course, V naught in this case will be the square root of minus alpha. And the state with a non-zero V naught is the non-zero velocity is the state where all these particles are moving coherently, moving together, is our flocking state. Now, this flocking state is a state, or moving state, is a state that now collectively, at the macro scale, breaks times reversal symmetry through this transition. Okay, is this kind of stuff actually seen in experiments? Well, if you look at bacteria suspensions, actually most of the time, bacteria or even epithelial cells or suspensions made of things extracted from living cells, in a large system, they actually exhibit a motion that is much more chaotic and with a lot of swirls and vortices, and in fact has been called active turbulence. Possibly a misnomer, because the behavior actually occurs in a regime in which dissipation greatly exceeds inertia, and the number that in fluids we use to characterize generally turbulence occurs in fluid, where something called the Reynolds number, which is essentially defined as a measure of the ratio of inertia to dissipative forces as measured, say, by shear viscosity. This number is generally very large, maybe order of 1,000 of larger when you see fluid turbulence. But in this system, bacteria are very big, and so the Reynolds number is essentially zero, and yet you get this turbulent-like motion. And what is very interesting is that we've been able to show that the vortex statistics in this vortex motion, in this turbulent motion, which is actually predicted if you do a nonlinear solution of the equation I just showed you, has actually some universal in scaling characteristics that are the same across all these different systems, bacteria, epithelial cells, and so on. And if you want to learn more about this, I refer to a couple of talks we had early on in the program by Jean-François Joanny and Luca Johnny. On the other hand, if you take the same bacterial suspension and confine it, say, to a ring, then you will indeed see the flocking state. It is coherent motion, which in this case will be going around the ring in some coherent way. And this has been seen in bacteria indeed, but also in this synthetic microswimmer that I said we call active colloids. In fact, various types of them. There are ones that swim by a variety of different mechanisms. So this equation, these standard two equations actually do predict some of the behavior we see in living and synthetic active matter systems. But another very interesting property they have is that they support sound waves. What do I mean by that? But first of all, these are systems, remember there was a nonlinear friction, so the momentum is not conserved. These are highly overdamped systems. And the presence of traveling waves in a highly overdamped system is surprising. In a fluid, sound waves arise from the competition of elasticity and inertia, the retardation between the two, essentially, and they arise because of momentum conservation. But in these flocking fluids, we actually see traveling waves, even though the dynamics is greatly overdamped, and we would expect a density fluctuation not to propagate, but simply to die out quickly due to dissipation. What happens here is that these traveling waves arise because since we have this phase transition to a state where all your particles will have a common swimming velocity V0, that's the direction of so-called spontaneously broken symmetry, a fluctuation from the direction of order associated with a deviation delta V perp of the velocity corresponds to what's called the Goldstone mode, and therefore is long-lived, just like momentum is in the system with the conservation law. And the fact meaning a fluctuation in delta V naught can decay just like in hydrodynamic mode, cost no energy because of the rotational invariance of the system. So sound waves arise from the coupling or the retardation in the coupling of two soft modes, just like in fluids, which are density fluctuation and the Goldstone mode fluctuation associated with the transverse velocity. And very roughly, if you take these two equations and linearize them in the frame where everybody is moving at the average velocity V naught, they will just look something like this. Fluctuations in the density are given by the gradient of fluctuation in this delta V perp, and fluctuations in delta V perp are proportional to gradient of pressures, which I can write as a derivative of the pressure calculated at the equilibrium pressure times gradient of fluctuations in the density. And clearly I can combine these two equations in a single wave equation for the density with a speed of sound that will be determined by, among other things, the stretch should be also not here. The speed of sound is determined by the speed at which this fluid flows. And so I have sound waves, and this is going to be important, might seem not surprising. What that means, a density fluctuation propagates much like a sound wave in a fluid. And this is going to be very important in a minute for seeing how topology comes into this picture. Just one more thing about the sound waves. The sound waves have actually been measured in this active one realization of this active colloid by Denis Barthelot at the University of Lyon. What do I mean? He actually measured the dispersion relation of the sound wave, the relationship between the frequency and the momentum. So it actually plots the frequency as a function of momentum here. I will find that, just like in a fluid, there is a linear dispersion relation with a speed of sound that is anisotropic. It depends on an angle theta, which is actually the angle between the direction V naught of mean motion and the wave vector. And this asymmetry, this dependence of the on the speed of sound, on the fact that you can have two different speeds of sound, arises because my original equations actually are not Galilean invariant, because they are equations, there is a reference frame. This is actually a fluid that is moving relative to substrate. So then you measure the dispersion relation, is indeed linear here, then it becomes nonlinear, and on the other side it might be something different. So we can actually quantitatively infer materials property of these moving fluids. Okay, so
Cristina,
I promised topology. Yes.
Let's pause for a moment. Looks like this is a good point to see if there's any questions from people not in the program. You know who you are. If you have a question, let's pause here for a moment. It sounds like this is a good point.
Christine, I wonder if there is kind of like analog of the second sound in this situation.
What's that? Sorry, say it again.
in superconductors there is two types of sound, right?
Yes, but this is not a superconductor. This is just a regular.
Right. So here there is no analog of second sound, right? I mean, in your example.
You're asking me if there is a second sound.
Yeah.
Well, in the simple model that I'm describing here, no.
Okay.
But there is actually a long story associated with that. I can tell you more about it.
Okay, thanks.
I have a naive question about why it's overdamped in the order state.
Well, the momentum, first of all, in this equation that I showed, that I wrote down here, you can see that V is a velocity, not a momentum, but let's say the density, and think of it as a momentum, is not conserved, right? You can think of this term as a friction, kind of a nonlinear friction. So momentum is not conserved in this system, okay? And now in the order state, it's kind of like a magnet. The length of the magnetization, it's not decays at a finite rate. The fluctuation, if you want to change the size of the fluctuation in the magnet of the magnetization, costs energy. A fluctuation in the direction of the magnetization in the order state does not cost energy because the direction of order is chosen spontaneously, and the system originally had a rotational symmetry. And the idea is that this is a model for, say, bacteria in a fluid, and so there is damping or friction coming from the surrounding medium. Active systems always move through a medium.
I see. So we really, so just consider the V0 into this equation doesn't give the friction. We need to add the fluctuation of the velocity.
Well, a sound wave it tells you about how, so there is the homogeneous steady state where V0 is non-zero. That's like a state of non-zero magnetization. Everybody is traveling in the same direction on average. A sound wave tells you how, if I create a local density fluctuations, how the density fluctuations evolves in time. In a system which is completely dissipative and damped with no momentum conservation, you would expect the density fluctuations to die out very quickly, not to propagate. In a fluid, the density fluctuation propagates. Those are sound waves, and that's because momentum is conserved and the propagation comes from the interplay of elasticity and inertia. This is a damped fluid, and it is surprising that the density fluctuation will propagate, but it does so because although momentum is not conserved, velocity undergoes a phase transition, and it's associated with a spontaneously broken symmetry and transfer fluctuations in the velocities, that is, fluctuations in the direction of motion, not in the magnitude of the velocity, but in the direction of motion, cost no energy. They are what is called the soft mode. And so it competes with density in allowing density fluctuations to propagate.
Mm-hmm. I see. Thank you.
Okay. Any other questions? Okay, so what I told you is that the fluid of polar swimmers has broken time reversal symmetry. And now I promised to say something about topology, so where does topology come in? And the way where you can actually see the role of topology here is if you either confine the system or place it on a curved surface. And what you can show is that when in this case, this fluid with broken time reversal symmetry behave like quantum Hall fluids, in the sense that not only they support sound waves, which is what I just told you, but they actually the sound waves become what are known as topologically protected modes, meaning they can propagate unidirectionally without backscattering, meaning without being disturbed by disorder at the sample edge. And this is something very closely related to what in quantum Hall systems, to the behavior of electrons in quantum Hall systems, and to what gives rise to the quantum Hall effect. Now, this might sound very mysterious, but I want to show you an example of how this can actually happen. So to see how that can happen, let's consider, imagine that one of these fluids with time reversal broken symmetry is actually confined to the surface of a sphere. Now, let's say take a sphere of radius r. Of course, the radius introduces now a new length or energy scale in the problem, and that will become quite important. Now, the first thing that happened is that if you look back at these equations called Toner 2 equations, these hydrodynamic equations on the surface of a sphere, remember there were various terms. First one was an advective term, and then other things on the other side of the equation. On the surface of a sphere, the first thing that you have to do is that you have to replace these gradients with covariant derivatives that acquire a gamma, Christopher symbol, where gamma is actually, in this case, related to the curvature, is related to 1 over the radius of the sphere. So more physically, what this does is that essentially, this advective term has a different, and this additional term ends up having a different side on the two hemispheres. Let's think of the equator here. Let's pick an equator. You have a northern hemisphere and the southern hemisphere. And what the advection yields is something like a Coriolis force that tends to push particles towards the equator, so it pushes towards the equator from the north and towards the equator from the south, and so because this Coriolis type term has different signs in the two hemispheres. The result is that when you put a flock on a sphere, of course, there is no way of getting a perfect uniform velocity for all the particles. And what you get is essentially a band of flocking fluid that wraps around the equator with a density that actually decreases at the two poles where it becomes very low and even zero. Now, because the Coriolis force, or this Coriolis-like force, has different signs on the two sides of the sphere, what happens is that the equator has to be thought of as the edge of the system. If I want to actually solve to find either the steady state or look at the fluctuations, I actually have to do it separately in the northern and southern hemisphere and treat the equator and then match the two solutions at the equator. So the equator serves like the edge of the boundary of the system. And so if you actually calculate the dispersion relation for these sound waves on the surface of the sphere by taking these Navier-Stokes type equations and linearizing them about the steady state, this band of flocking particle around the sphere, what you find is the following. So here is my sphere. Here is the equator, one equator that I've chosen here. Let me take an angle here, a latitude that measures the distance from the equator, if you like. I measure the dispersion relation and I calculate the dispersion relation. If I'm away from the equator, the dispersion relation, omega as a function of wave vector, I find that actually there is a gap. So the dispersion relation of my sound waves is supposed to be linear down here near the origin, but it looks something like this. And there is actually a gap, meaning there is a region of frequency where sound waves cannot propagate. And this gap is actually proportional to it depends on the distance from the equator, and it depends on the radius of curvature of the sphere. Right at the equator, theta corresponding to theta equal pi over 2, the gap vanishes, and the two sound waves meet at a common point. So what I find is that the curvature really changes the dispersion relation of my sound waves. It creates a gap for the propagation of the sound waves anywhere in the bulk away from the equator, and the sound waves are only allowed to propagate at the edge. As a result of this, what happens is that if I excite a density fluctuation, plug the system and excite a density fluctuation on the equator, this density fluctuation propagates undisturbed and unidirectionally in the direction that is dictated by the broken time reversal symmetry of the system, propagates unidirectionally along the equator. It cannot turn around because the system has time reversal symmetry. It's not allowed to travel in the other direction. It's broken time reversal symmetry. It cannot scatter into the bulk because sound waves cannot propagate into the bulk, which is here is either the northern or the southern hemisphere. And therefore, it turns out to be what's called a topologically protected mode. In fact, you think about the integer quantum Hall effect, there what you have is that the conductance of electrons is quantized, is an integer, and cannot be changed by a small perturbation because of this quantization. Similarly, what happens here is that these sound modes actually have a conserved charge, we could call it, which is called the Chern number, and cannot be changed, therefore, by continuous deformation, and therefore are protected from coupling and scattering into the bulk. So these systems, just like charged quantum particle in a magnetic field, these time reverse broken fluids have topologically protected state. Now, I think Lars asked me to be short, but we did start a little late. So let me just show you one more example of the same thing, of this topological protection in the system.
Cristina,
Yes, is there a question? Yeah.
Yeah, let's consider the limit when R goes to 0. Then it's only this protected mode exists.
The gap, sorry, R going to 0.
Yeah.
Well, then I think the gap, I don't know, the gap becomes really large.
Right, but the protected mode is still there, right?
It should still exist in the limit of very small r, it should still exist, yes. Now, I don't no longer even have a system in the limit r going to 0, so I'm not sure what exactly means. Now, in the limit of small r, certainly yes. Yeah.
Okay.
Any other question? So, and that was work, by the way, done with Mark Bowick, who is here at KITP, and a very good student, Suraj Shankar, who is now at Harvard. Let's consider a different example. Forget the sphere. After all, there are not many cases in which bacteria swim on the surface of spheres, although certainly they do swim on curved surfaces. But let's think of something slightly different. Imagine having many of these rings in which you construct a device like the one shown here, where effectively I have 4 rings filled with bacteria or with these micro swimmers, artificially engineered epic colloids, or the one to the right, where I actually have these circular chambers connected by these pipes to which bacteria are allowed to flow. Both cases, I have square lattice, I create square lattices of circulating currents. And you can actually show that at least for certain values of the spacing here of these channels, what you will find is essentially an alternating clockwise and counterclockwise rotating current. Essentially, you get antiferromagnetic order of the circulating current. You can quite see it here. This is actually an experiment carried out a few years ago in the lab of Ray Goldstein at Cambridge. So the arrows actually are bacteria tracked by something called particle image velocimetry. And I can see the arrows, so I'm redrawing them for you. This is really a lattice of alternating current, and the whole system is much bigger, and is actually perfect antiferromagnetic order. So what happens here is that if you have a square lattice of circulating currents, in some sense you're restoring time reversal symmetry at the global scales, because for the whole system you have as many currents going to the right as currents going to the left. But now, if you have a different lattice, one that perhaps like here in the upper corner has an odd number of circulating current per unit cell, and this was realized in this structure here called a Lieb lattice. This is work by Vincenzo Vitelli and collaborator at the University of Chicago. Then what you get here is something quite more complex. First of all, the structure of the steady state of clockwise and counterclockwise circulating currents is quite a bit more complicated. It's not what is shown here. But on average, the system has a net chirality, as a net circulating current. And now, if you actually excite now a density fluctuation at the edge of the system, what is shown here is the behavior of such a density fluctuation. The color is the deviation of the density from the equilibrium value, with yellow being low and red being high. So what you see here is that density fluctuation, first of all, is localized at the edge of the system. First of all, if this was a movie, you would actually see the density fluctuation travel around the edge in the direction of the net chirality of the system. And what we have here is sort of like an imperfection of the lattice, is an obstacle, and the density fluctuation will travel around the obstacle undisturbed. So again, it's another example here of a topologically protected edge mode in a fluid where density fluctuation propagating at the edge travel unidirectionally. They cannot backscatter because they cannot go into the bulk, because again, this is a system that propagates a gap for the propagation of density waves in the bulk due to the complicated lattice structure. And they can travel through obstacles without being backscattered, because due to the broken time reversal symmetry, they cannot travel backwards. So these systems, these fluids with broken time reversal symmetry exhibit, interestingly, some of the same behavior, again, as quantum particles, charged quantum particles or electron fluids in materials that has been studied quite extensively now for some time. This is one of the things that our program has been thinking about. I just thought I would end by highlighting some of the many questions we've been discussing and trying to make some progress on in these past 8 weeks of this virtual program. Often active systems of the type that I described have effective interactions that are non-reciprocal. That is, in some sense, you could say, break Newton's third law. This clearly happens all the time in living systems, but also in these active colloids, where the interactions are mediated by chemical reactions. If you have a mixture of two different types of active colloids, then the effective interaction described by the chemical interaction will be non-reciprocal. So understanding the statistical mechanics of these systems that have broken time reversal symmetry at the microscale and non-reciprocal interaction is something we are now actively working on. I haven't said anything about chirality, although some of what I said is related, but a lot of these systems, a lot of active particles are chiral and form microscopically chiral states. But one could even ask, a perhaps more interesting question is, can we actually have emergent chirality from a collection of interacting achiral objects? So how does chirality emerge as a collective property? Many of us are working on understanding living tissue, collection of cells as materials, and trying to understand whether we can describe them as liquids, or whether or when, I should say, describe them as liquids or solids, and develop a continuum theory that somehow has to merge continuum mechanics with reaction diffusion equations, because the behavior here is clearly determined by the interplay between biochemical signaling and the transitional mechanical forces. Another thing that there's been a lot of activity on is actually more, and now we are actually going more in the direction. Remember, I said nothing about thermodynamics, but thermodynamics of active systems is one of the focus of the program. And some of the questions we're struggling with is, how do we quantify activity, or how far a system is from equilibrium? How can we measure that? Or related, how can we actually tell when time reversal symmetry is broken from the data? Of course, if you drop a glass on the floor, clearly you know that's a process that has broken time reversal symmetry. If you see a movie of a dividing cell, you know that that direction in which the process is going is one that breaks time reversal symmetry. But there are a lot of smaller scale motion inside cells where it's much harder to tell. And some of us are trying to develop measurements of the breaking of time reversal symmetry through new ways of analyzing imaging data taken inside cells. Can we develop an effective thermodynamics of active systems? Can we quantify energy consumption? How much energy does it take to keep bacteria moving? And this is really important for understanding the metabolism of living systems. And then finally, perhaps we should go back a minute to the question of why does it matter? Is any of this relevant to biology? Well, there has been a lot of progress in directions, for instance, on tissues that I think has been very, has had quite a big impact on biology. So I'd like to think that the answer to that question is that yes, there is relevance to biology. And then finally, can we actually tell active matter what to do? Meaning, can we learn how to control activity, perhaps through this synthetic active system, so that we can actually engineer new materials and new functionality? That's a direction in which actually both theory and experimentalists are doing a lot of work. So with that, I hope I have convinced you that this is an interesting field, and that is why many of us actually, almost 100 every day, are spending quite a bit of time listening to talks and discussing this topic, and I hope maybe there'll be some more questions. Thank you.
Great. Thank you, Cristina. I can hear the applause. Okay, questions, please.
I have a question for me. So, first of all, thank you for a very accessible talk. This is great. I was wondering whether the waves, the sound waves analogy that you, why don't they suffer from something like an equivalent of Landau damping?
Well, first of all, I wouldn't call it an analogy. I mean, maybe you don't.
It is on a, right.
Okay, it's not, perhaps the frequency is not in the spectrum of sound, but the reason I say I wouldn't necessarily call it an analogy is just because, there are pressure or density fluctuations that are traveling, so that's why we call it sound waves. But yes, anyway, sorry. But what do you mean exactly? I don't quite understand what you mean when you say describe it as Landau.
Well, it's a collective behavior.
Yes.
And it's made up of constituent particles, and the particles have noise. So that noise will try to diminish that collective behavior, and therefore cause a damping of the waves, of the movement.
Oh, there is damping. If you're asking me if there is damping, yes, there is damping.
And is it damping that is in the sense of a Landau damping? Is it more a viscous kind of damping?
It's a damping in the sense of viscous damping, because these are there is viscosity in the system. So there is damping in the sense of viscous damping, and in fact, the topologically protected modes that I described on the surface of the spheres are actually damped.
But if you say it's a viscous damping, then I think in terms of actual true collisions.
Yes.
So
well,
are these bacteria actually colliding, or are they trying to avoid contact, and that is inherently what is leading to it?
Well, there is viscous damping. This bacteria, first of all, assume into a fluid. And this kind of model that I described is actually appropriate, works well at very high density of bacteria, because if you're at a lower density, you really should do a two-fluid description where you describe both the bacteria and the fluid. So the bacteria, you could say, yes, they are colliding with each other, but viscous damping is really, exchange of dissipation momentum at the interface between shearing layer of fluids, or if you want to think microscopically, you could think of it as colliding particles. But yeah, it is viscous damping, indeed.
Okay, thank you.
Hi, Cristina. This is Boris. Can I ask you a question? Can you hear me?
Yeah.
Can you comment on similarity or difference of these topologically protected? Hello?
I think I lost you, Boris. You said, can you comment on similarities or differences? And then I lost you.
Okay, in this active matter versus just flow on rotating sphere, right? There are these Kelvin equatorial waves, Kelvin waves that people talk about in the context of geophysical fluid mechanics.
Yes. Mm-hmm. They're quite, so indeed, there is this work that Boris is referring to on sort of geophysical waves at the surface of the Earth in the atmosphere. Kelvin
Brad
waves.
Marston gave a couple of talks about it.
Which, yes, absolutely. And it's actually very similar. So in that case, the rotation is the rotation of the Earth. So it's imposed from the outside. In our case, the rotation is intrinsic to the system. There are differences in the excitation spectrum and in the number of topologically protected nodes, but but it's a very similar phenomenon. And in that sense, that's why we call our advective force Coriolis force, if you like, precisely inspired by that work. Yes.
Okay, I'm not seeing other questions. Any other questions from the clusters people? Thank you, Frank, for being out there.
I just had a question about if you set the sphere rotating about the same axis, for example, to generate a Coriolis force of comparable magnitude but opposing direction.
Well, I don't know. Perhaps I would kill this effect. That's an interesting question. I haven't thought about it, but yeah, if you generate an extra Coriolis force which is equal and opposite, then I would imagine you would no longer have these. Yeah, I would imagine you no longer have this effect, but I'm not sure. I haven't thought about it.
I could ask another question that's much more difficult, but do you see any analogy to a star, which is effectively just a sphere, a rotating sphere of fluid?
I would think so. I would think there should be. Because as the work that Boris mentioned, which is actually published, was done by Brad Marston from Brown and some French scientists. It actually shows that there are certain atmospheric waves that have been known for a long time on the surface of the Earth. And as I said, I think some are called Kelvin waves or Yanai waves or something like that. And that these are topologically protected nodes in the sense in which we just described. So I don't see why that wouldn't apply to the surface of a rotating star.
It'd be really cool to try to.
This is, of course, first of all, it's a very vague answer I'm giving you. And secondly, well, I don't know how would you do an experiment about that.
Well, I mean, you could try to make predictions for observable features in stars, and then we could actually go and look for them.
Yes, that is totally true. But yeah.
I don't know, maybe Lars has more to say about that.
No, well, I think Brad's work highlighted these modes that were known from atmospheric physics and studied going way back to Laplace for the tidal deformation of the Earth's atmosphere due to the moon. Waves that are mostly transverse to gravity, but therefore, as they get near the pole, get a very large transverse Coriolis force that keeps them at the equator. Sort of as you go up from the equator towards the pole, there's a turning point and they stay in the equatorial region. So that's a set of trap modes that we're still looking for in stars. So,
but supposedly they're more than just trap modes. They actually have these qualities called topological protection that really prevents them from mixing with other bulk modes in the bulk of the hemisphere.
yeah.
What would you look for? Strong differential rotation or some gradient in your differential rotation that may be attributable to something like this?
Well, ideally, if there was some large imperfection or obstacles on the surface of your star, you should be able to see if it goes through undisturbed or not. Although I don't know if I realize you cannot do that.
I think we should see if there's any other questions.
I don't know.
Okay, well, thank you, Cristina. Fantastic job. Really appreciate your effort. Everybody enjoyed hearing what's going on in active matter, and I think I'm going to sign off. Thanks to everyone.
Thank you.